zeroing, and I was like, wait a second.
I'm like, I don't know if I walked through.
Gosh, dang it.
See, chemists are so specific and we're tricky like that. We'll throw you milliliters and then you have to plug it into a formula that involves liters, and if you don't change it. And in gas laws, you have to work it all in the problems and then work it backwards.
Yeah.
And some of these, if you work it in milliliters straight through in the answers in mils, you can keep it because its ratios and proportions works out. So until you get that experience, I would always change the milliliters and use milliliters.
Yeah.
Chemistry. It looks like AI.
All right, thermochemistry. This is one of my favorite chapters to teach. I love thermo. I used to not like it. I used to not like thermochemistry. I felt it was this weird little singleton chapter that was thrown in the middle of the book that really didn't have a lot of connection previous and post chapter 5. Well, after I went through some courses in my PhD program, I recognized that energy is a thread that goes through all disciplines: physics, chemistry, biology, geology. We all talk about energy, and energy is at the root of thermochemistry. And so I completely changed the way that I teach. Now, thermochemistry is actually a very essential component in this course and beyond into Chem 152. Thermochemistry is super important to everybody who's in this class, whether you're in here to be an engineer, medical person, a scientist of any kind. Energy exchange is essential and goes across all different disciplines. The physicists like to classify energy into different categories, and the engineers tend to adopt a lot of what the physicists do because they tend to work in real time. So physicists and engineers talk about energy in terms of chemical, radiant, thermal, etc., etc. And then what they'll do is they'll go to great lengths to show you a machine and how the mechanical energy of that machine is influenced by the thermal pollution and eventually the output of what that machine can use. Well, chemists, we look at things a little bit differently in terms of energy than the physicists and the engineers. The physicists and the engineers discuss energy in terms of the work that it can do. Well, that's because the physicists and the engineers discuss energy in terms of a closed system, meaning there's no energy or exchanges in and out of a system. And so a system can do work if it's closed, because if the system expands, then say, for example, it's an automobile engine and you're combusting fuel in a piston, and the combustion is a chemical reaction that causes the piston to move because of the expansion of the gases inside the chamber where the gasoline is combusted. So you're actually taking chemical energy and you're changing it into mechanical energy that can be changed into kinetic energy, the movement of the vehicle. And so that's the way the engineers talk about it. They discuss closed systems. But often in chemistry, we don't have a closed system. We've got a beaker of stuff that's getting warmer or colder, and we can measure the degree of temperature change, but we often can't measure it directly. So this idea of energy in terms of physicists and engineers is they like to transfer and talk about work. Now, I don't talk in my class a lot about the work. Now, the textbook, chapter 5, Brown and LeMay will discuss this because that is the background, and the physicists and the engineers would say you really have to understand that the work is being done, and that's why the energy is being transferred. But for this class, we're going to relate it more to heat energy than we are to work energy, because that's something that's actually easier to measure. Now, this idea of kinetic versus potential energy, and textbooks always give you this classic example that there's a person riding a bike down a hill, or you've got a boulder and you're getting ready to roll a boulder down the hill, and they say the person on the bike or the boulder at the top of the hill has the maximum potential energy, meaning by virtue of their position at the top of this hill, that they have the potential to do work as they move down the hill, and they could hit something, it could move it, and work is actually basically something has to move, all right? So you could expend some of the potential energy that this bicyclist had at the top of the hill through work, movement down the hill, and then as they go down the hill, the potential energy would decrease as the kinetic energy increases. So if we define these two major categories of energy, we can subdivide those categories in chemistry and physics and engineering. The two major categories of energy that you can cross-discipline divide them up into is kinetic versus potential. And let's think about kinetic energy as the energy of movement. All particles, all molecules in chemistry have some sort of kinetic energy because they're all moving. Even solids have kinetic energy. Solids have what we call vibrational movement. They are moving around a fixed point, but they're still vibrating. So something that's a solid, a piece of plastic, a piece of wood, a piece of metal, and you say, well, gosh, it's not moving, it's not a liquid, it's not viscous, but the particles, if you can look at them from a microscopic perspective, are actually vibrating around that fixed point. So they do have kinetic energy. Then when kinetic energy increases, the movement of the particles increases as temperature increases. We can add heat energy to a substance. Those particles in the solid are going to start vibrating faster and faster. As they vibrate faster and faster, they're going to break the bonds that hold them as a crystal solid. And once they break those bonds that hold them as a crystal solid, they transfer into the liquid state. And what that does is it stores some of the energy. When you change the phase of a substance, say for example you're going from a solid to a liquid, and I'm actually going to use an illustration that I think helps relate this a little bit better, and a story. Chemistry teachers like to use stories a lot when they're discussing things you can't see, because stories relate things you can't see to things that you are used to seeing. Why is that not working on the screen here? All right, we want the laptop, which we have. And why is it not giving me the ladybug? Oh, computer. Oh, I know why. It's the PowerPoint thing. Okay. There we go. All right. College teaches you to be persistent. All right. Back when I was a high school teacher, I used to introduce this topic with a boiling water lab. I would have students take a beaker of water, and they would take a thermometer, and we would freeze it in the column of water in the freezer. And so it was suspended in ice. Then they would take the beaker, and they would put the beaker on a hot plate and turn it on hot. So we're adding thermal energy in the form of kinetic. And in chemistry, we're going to call energy that is thermal energy E sub TH. So in chemistry in this class, I like to classify energy in 3 different categories: energy thermal, energy chemical, and energy potential. These two, if we were to subdivide them, this would be more of the kinetic energy variety. This would be more of the potential energy variety. So if we have a big umbrella of all kinds of energy, physicists would classify things as either kinetic or potential. The things that we like to talk about in chemistry, they could be subdivided even a little bit further. All right, so at this point, the ice does not have a lot of kinetic energy. It has some, because we've got the little ice crystals in a crystal structure, whatever that happens to be with water, and they're vibrating around their fixed points. So we might have a little molecule at each one of these junctures, and they're vibrating back and forth and up and down and in 3 dimensions, but they cannot leave the fixed point. So we add kinetic energy, we add heat energy to the ice. So these particles start moving around faster and faster and faster until they're able to break these bonds that hold them as a solid. And then all of a sudden, now they're in liquid form. If we took and we graphed this, and we said, okay, over time, we could say in this direction, we might even have units of something like seconds on the horizontal axis. And in science, we always put the independent variable on the horizontal axis, the thing that we are changing. In this case, I'm adding heat to my experiment. And the dependent variable, the thing that I'm measuring as a result of the thing that I'm changing, goes along the vertical axis. In this case, it would be the temperature, and the units would probably be in degrees Celsius. So we would say this is a time temperature graph for the heating of the ice. Now we know that ice freezes at 0 and water boils at 100. So before I put the energy into this, and I had the thermometer, and I took the temperature, if I'm eyeballing this, and I took the temperature, what would the temperature read prior to me adding some heat energy into this? Everybody thinks ice is at 0, but in fact, ice can get much colder than 0. 0 is when it freezes. But ice as a solid can get much lower than 0 degrees as long as it stays a solid. So we're going to say it starts out somewhere below here, below 0, this is the temperature of the ice. So it takes some energy to heat up the ice till it gets to 0 degrees. So I'm adding heat energy. It's not melting at all. Visually, I'm not seeing the ice melting at all. But once it gets to 0 degrees, visually, then what would I see happening at that point in time? Well, I'd see some condensation because on the outside, especially in Arizona because it's really cold. But what would I see going on inside the beaker? It starts to melt. Okay, at this point, it would begin to melt, which is super important observation to make at this point in time. Now, the temperature, once it starts to melt, would not change significantly until what happens a little bit later. All the ice melts. So at this point, it begins to melt. At this point, all ice is melted. Once all the ice is melted and it's all turned to a liquid, so this was when it was all a solid. This is the phase change between solid to liquid. Once it's completely a liquid, then we would see the temperature start to rise, and it would make a nice inclined plane with a very specific slope. And as long as I didn't change the temperature, that slope would be consistent as long as I kept heating it up. So this would be when it's completely a liquid. Well, if I was adding thermal heat energy at this point in the experiment, where is that energy going? Because it's not going to heat up the ice. The break bonds of what? The solid to turn it into a liquid. That phase change energy, which is a variety of potential energy, it's stored in the position of the molecule and the movements of the molecule. And here's why. As a solid, a substance only has vibrational movement. We say it only has one mode of movement, and that is vibrational. Engineers, this is super important to you guys. When it changes into a liquid, we store some of that energy into position of the molecule, and it changes from the simple vibrational movement to two modes of movement, vibrational as well as rotation. So now you have two ways for that molecule to absorb radiant or kinetic energy. It can absorb it by vibrating it, and as liquid molecules get warmer and warmer, they start vibrating faster and faster. But as liquid molecules get warmer and warmer, they also start to rotate a whole lot more. So you have two modes of movement as a liquid. So we say a liquid has higher heat energy, not only because it's at a higher temperature, but because it has two modes of movement as those particles are moving around. Well, then once it gets to about 100 degrees, what would you visually see happening at this point? It would start to vaporize, right? We see some water vapors coming up off of my boiling water, but what else would we see? Well, the graph would absolutely begin to plateau, but what else would we see happening macroscopically in our beaker?
Level go down.
The water level would go down, absolutely, but more importantly than that, what else would we see? Bubbles. And where would those bubbles be originating? At the bottom. All right. So if we could get down there, down to the level of a molecule, and we looked at what's causing those bubbles right there. What's causing those bubbles? And this is a huge misconception in science. So if you tell me the wrong thing, that's okay, because everybody thinks this.
Well, wouldn't it just be the same concept as ice going to solid? Heat is breaking up those bonds.
What bonds? Okay, here's the misconception, and I'm going to throw you under the bus, my friend, because you volunteered. Here's the misconception. What bonds are we talking about?
I was going to say the bonds between the water molecules that they liquid.
I like that better. You're not under the wheels yet. Keep going.
Well, you break them up and then now.
Break up the water molecules that hydrogen and oxygen break up?
No,
No. Good. Thank
they
you.
stay together as water molecules.
Okay. Keep going.
But it's kind of hard to explain.
The hydrogen bonds. Remember, if you remember hydrogen bonds, those, because water is a very polar molecule, right? It's got a positive and a negative end. They're like little magnets. And we call that magnetism, and I'm putting that in air quotes. It's not really magnetism like a metal is magnetic, but it's a polar thing, and so they're attracted to each other. So you're right, there is some bond breaking in there, but I don't want you to think that hydrogen and oxygen are breaking up. Let me show you something that I find hilarious that I sent to a colleague this morning that you guys are going to die when you see this. It was an ad I found from Land's End. and it perpetuates this idea that is a common misconception in science. All right, so let's look at, this is for long underwear. See, there's some cute models modeling the long underwear. We don't wear this in Arizona, right? We don't need long underwear. But in cold climates, they put long underwear under their clothes because it's so doggone cold. Well, I love this. Look at this. Look at this diagram. Here's what this long underwear does. The manufacturer claims that it takes the water molecules and it wicks them away from your skin. And as it's wicking them away from your skin, it's breaking them up into hydrogen and oxygen. If that was true, I would not wear this underwear around an open flame.
Oh, yeah, that'd be fun.
Why would I not wear this underwear around an open flame? It's making hydrogen gas, and hydrogen gas is explosive. So this is a good example of common misconceptions in science and how they are perpetuated. Underwear does not break the bonds between hydrogen and oxygen molecules. Boiling water, you're not liberating hydrogen and oxygen gas from water. People think that the steam that's coming out is water breaking up into hydrogen and oxygen. If that were true, I would not boil water on a gas-powered stove. Because what's on a gas-powered stove? Fire, an open flame, and if you've got hydrogen, which is explosive, and oxygen, which supports combustion, together, you're going to have a mini space shuttle. Right? All right, so there's the disclaimer. There's the disclaimer. We'll talk more about this on Thursday.
Why can't you light water vapor on fire?
Yeah.
That means